Good morning. We are in the last phase of the last but 1 week. So, we are going to discuss maxima and minima functions of two variables. This is very important, because maximization and minimization comes everywhere, whether you study physics or engineering or even medicine or biology, does not matter. You have to deal with the issue of maximizing or minimizing function. In fact, one of the all time greatest mathematician Euler, whose notation dy dx you actually use and whose formalisms that you see in many places are due to him, had a statement that nothing in this world happens without a function being maximized or minimized. So, this is a very important thing, but because real life modeling is largely with functions of more than one variable. Basically, we are talking about, I will just talk in terms of minimization. You can also talk in terms of maximization, does not matter. I will write everything for a minima, but you can write everything for a maxima if you want as a game. So, just like in the case for real variables, one real variable, here when I am talking about a minimizer, I am essentially what I have to be clear what I am essentially looking for, whether I am looking for a local minimizer, any x which gives you the minimum xy pair which gives you the minimum value of this function would be a local minimizer, or you are looking for a global minimizer. Similarly, in this case global or local maximizers. So, what do you mean by a local minimizer? For example, if you have a function like this, say it is not so easy to draw a graph of 3-dimensional graph here, something like this. So, think that this is a 3-dimensional contour and this is the xyz axis. So, how you see here also this point is some sort of a minimizer, but over some given region. Here this is a minimizer over this region, but this could be a global minimizer of this function also. So, we essentially have to deal with local minimizers. Some cases they become global minimizers. So, a local minimizer is what? So, x bar y bar is called a local minimizer. So, this function f, sometimes if you want to write a function of two variables, you can write it as a function from R2 to R, where R2 is nothing but a symbolism of the plane, just telling you that every point in that plane is given by a pair of real numbers, called a local minimizer of f. If there exists a delta greater than 0 such that for all xy satisfying x minus x bar whole square plus y minus y bar whole square, the distance between x y and x bar y bar satisfying this, we have f of x y is greater than equal to f of x bar y bar. If this relation holds, so x bar y bar is called a strict local minimum. This concept you will not find in standard calculus textbooks, but that is what actually happens when you do a second order check, which you will soon see. So, it is called a strict local minimizer if everything else is satisfied, if we have f of x y strictly greater than f of x bar y bar. Of course, local means they have to satisfy this, there must be some delta for which this happens, for all x y which is not equal to x bar y bar. Okay. Now, how do I detect, how do I really start trying to find a minima? We are not going to draw graphs and look at the graphs, not even the modern mathematical softwares can actually give you a vision of the graph from R2 to R. They cannot map it for whole of R2, you essentially map it for a part of the R2, a part of the domain, and then you look at it. So, what you can find, even if you declare some point as a global minima, that could be actually a local minimizer as a whole. So, essentially there must be some other ways and analytic ways of finding them. We have already studied analytic ways of finding them in our course in or class in the calculus of when we are talking about the maximum minimum of functions of one variable. So, we know that if a function of one variable has a minimizer at x bar, then f dash of x bar must be equal to 0. Could we try out some sort of thing like that? So, now suppose x bar y bar is the solution. Then and f is differentiable. So, when f is differentiable, somebody says that it is differentiable. This term differentiability is not so simple when you functions of two variables, but for all of our work and all of the usual practical work in calculus, this means f has the partial derivatives, f has all the partial derivatives and they are continuous, all the first partial derivatives and they are continuous, means the first partial derivatives are continuous as a function of x y. CONT is short for continuous. So, essentially that is the meaning. So, then if this happens, then x bar y bar must follow this condition. Okay. X bar y bar must follow this condition, that is you should have del of del x computed at x bar y bar, that must give you 0, and del f del y at x bar y bar, that must give you 0. Let us consider the function f of x y. Let us test this, that whether it is actually happening, x square plus y square. You can understand that the x square plus y square is always, this function is anyway always greater than equal to 0, and if I put x equal to 0 and y equal to 0, the function value would be 0. So, here x bar y bar is equal to 0 0 is the minimizer. But you see, if you take del of del f x, it is 2x, and del of del f del f of y is, or del del y of f is 2y, and this implies that del of del x at the point 0 0 is 0, and del of del y, you just put x equal to 0 or y equal to 0 there, at the point 0 0 is also 0, which validates what we have said, but these are just necessary conditions and need not be sufficient, right. For example, if you take f x y equal to x square minus y square, then find the points where this would be satisfied. So, we are trying to find points where this will hold. So, this will again lead me to the equation 2x equal to 0 and minus 2y equal to 0, which would again imply that the only point where the function, the partial derivatives vanish is x bar equal to 0 and y bar equal to 0. but if you draw the graph of this function, which is called the saddle graph, something like this. So, what you see, I have obviously not drawn the graph very well. So, this is called a saddle graph. So, this point x 0 y 0, you know, this is minimizing this curve along the y axis, but maximizing the curve along the x axis. So, it is maximizing the function along the x axis and minimizing the curve along the y axis. So, such points are called saddle points, which may also occur sometimes. So, you see x bar x 0 y 0, here x bar y bar equal to 0 0 is not truly a minimizer, but it satisfies the necessary condition, satisfies this condition of the gradient being equal to 0. So, this condition is only a necessary condition and not a sufficient condition. Now, is there any way, is there a way to talk about sufficiency when if we invoke second order derivatives in the case of functions of one real variable? So, now we look at the sufficient conditions. So, what we are now going to do is we are going to list down the second order conditions which are required to be checked at a critical point. Now, suppose you have a point where, say you have a point a b such that the derivative of a b equal to 0, the partial derivative is 0. Now, I am going to make a check, assuming that the function is now twice differentiable or twice continuously differentiable if you want, whether I do have some, whether we can have some conclusion about what is the true nature of a b. So, number 1, so if you have this, so if at a b you have the following, that del 2 f del x 2 is strictly less than 0 and del 2 f del x 2 del 2 f del y 2, I am assuming all of these are continuous, because then I can have that del 2 f del x del y and del 2 f del y del x is same, like we had discussed in the last class. So, if at a b these quantities are found to be greater than 0, then a b is a strict local maximizer. This word strict is not mentioned in the calculus books, but it is actually like that. If at a b you have this one, so I am not going to the details of the proofs. So, you just learn it as a working rule for the moment. Then a b is a strict local minimizer. Now, if at a b you have no information on this, so it could be 0 for example, you just have the following information, for example, this could be 0, but you have, if you now if you have the following, that and you have no other information at A B, then A B is a saddle point. So, what do you mean by a saddle point? Saddle point means, so if I instead of if I fix my y and I put the value of y as b, then this becomes a function of x, and then as a function of x at the point A, the function is either maximized or minimized, and conversely if I put a in the in place of x in the function and then it becomes a function of y, then at the point B it is either maximized or minimized. So, if it is maximized along x, it will be minimized along y, if it is minimized along x, it will be maximized along y. Such points are called saddle points. The usual definition given, for example, in Thomas and Finney, that if you take a point around, in one side you will find the function value is going down and one side you find the function value is going up, is not really a very logical definition, at least to me. I do not find the definition very interesting. In that sense, every point will really become a saddle point. So, the true nature of the saddle, if you look at the thing here, so if this is my x axis, this is my y axis and this is my z axis. So, you see if I fix up the value, so take this point 0 0. So, at the point 0 0, this is a very crucial point, at this point 0 0 at the origin here, if I, this is my origin, if I fix the value 0 and put it here, put y equal to 0. If I put y equal to 0, then what is happening? At x equal to 0, x square is getting, the function x square is getting minimized. If I put now x equal to 0, then at y equal to 0, at y equal to 0, the function minus y square is getting maximized. So, if you look at this function, so that's a very important thing, that you have now put x equal to 0, x is now look at what is the nature of the function, and then that is of this form minus y square, and then so then the z values are nothing but z becomes minus of y square. So, it is of this form and it is getting maximized at 0. So, it usually what happens is a saddle point in optimization is always said to be a point where when you are fixing up the x value, then it is maximized along y, and if you fix up the y value, it is minimized along x. Okay. So, this is a very crucial point. The saddle point has to have that property, that if you fix the x, that is you put one of the value critical point values and if of x, and then as a function of y it will get minimized as a maximized in the other critical value, and if you put a function of, if you put say y equal to for example y equal to, if you put the value of y, the critical value of y, then as a function of x it will get minimized at the critical value of x, and this is a very crucial point to understand, not the definition where they have given that you have to look around and see whether it is at one point it is increasing, at one point it is decreasing, but the crucial fact is that this sort of thing is happening at a saddle point. So, every point is really not a saddle point when you are coming to functions of two variables, but when you are in functions of one variable, for example like this, so for f(x) equal to x cube. So, a point is either a local minima, global minima, or a point of this form, but the function is changing its, curve is changing its shape, that these sort of points are called points of inflection, and these a critical point has to be any of the three, local global minima or local global maxima or a point of inflection, it cannot be anything else, but such a thing can happen if your function, if you are in the function of two variables. See, if you have a function of two variables, take an example f of x y is equal to y minus 1 whole square plus x a cube. So, here if you do grad f x y equal grad f x y, you simply get 3x square and 2y minus 1, and so x bar is equal to 0 and y bar equal to 1 is the only critical point, but this critical point, suppose you put, it is neither a local minima or a global minima or a local maxima or a global maxima. Now, you put x bar equal to 0. So, you have y minus 1 square now. So, y minus 1 square does not get maximized at y bar equal to 1, it get minimized at y bar equal to 1. And if you put say x bar y bar equal to 1, then you have x a cube, and you know that x a cube does not get minimized at x bar equal to 0. We have just drawn the graph of x a cube in the last page. So, you see immediately that this point cannot be a saddle point. So, there are functions where there are critical points, and the only critical point which are neither local minima nor local maxima or global minima, global maxima, or even a saddle point is just a critical point. This is the major difference between the study of maximization minimization in one variable and to maximization minimization in two variables, and this is absolutely critical. I am just giving the saddle point idea is critical. I am sure that you can compute out these things and look at any examples from the book, and if you have any questions, my TAs will answer you on the forum. But for example, if you take the function f x y equal to x y, so here x is, so if you take grad f x y equal to 0 0, so then you will have y bar x bar equal to 0 0, right. So here what will you have? So here what is the issue here? Here you have y, here you have x. So here also you have 0 0 as the critical point. Now what would happen if I put 0? You know very well, if you draw this graph is a slightly strangish graph. It is also, it does not, again you can see the picture in the book of Thomas's calculus. You will observe that at the point 0 0, if I put x equal to 0, then the function becomes 0. So basically then it is a 0 function, it will be maximized at 0, it is a trivial thing, but it is again it will be minimized if you put y equal to x equal to 0, then it will again be maximized at y equal to 0. You can say okay, I can put any value of y and that will maximize it, but no, I am just looking at the point 0 0. So at the point 0 0 it will be doing both the things, but if you put 0 0 it is 0, but if I put 0 minus 1, this will, if I put 1 and minus 1, it will have a negative value. So you see these are not local maximizer or global maximizer, but is a saddle point. So it is very important to keep in view that, for example, here that this could be a critical point without being a saddle point, but this is an obvious saddle point, while in the earlier case here this saddle point had some more information, it was giving you more information about how it is not, this is not a trivial saddle point, while the other one, this one, this case f of x y, f x y equal to x y 0 0 is a trivial saddle point. But here again you have to concentrate on this example which I have given, where the only critical point is neither a saddle point nor a global or local maximum. So we would end it here, and thank you very much.